Hello, ladies and gentlemen. My name is Adam Whittle. I'm the Marketing Manager at Brookes Bell. Thank you for joining our webinar on ship powering today. Our presenters today are Doctors Kieran Dodworth and Bogdan Ganea. And their presentation will hopefully give you more of an understanding of performance clauses in shipbuilding contracts and specifications. The presentation today will last approximately for 40 minutes and will be followed by a Q&A session. Please feel free throughout the presentation to put your questions in at any point using the Q&A text facility, but all questions will be put to our presenters at the end. So without further ado, I'll hand you over to Kieran.
Thanks very much, Adam. So by way of short introduction, my name's Kieran Dodworth. I'm Director of Naval Architecture here at Brookes Bell, and also one of the consultants. I have a background in hydrodynamics. My PhD is in that subject, and I've been a consultant for around 20 years. And one of the types of consulting which I often get involved with is about ships and their performance, verification, sea trials, etc., which is the subject of this presentation. I'm joined today by my colleague, Dr. Ganea, who, before joining Brookes Bell in 2008, was a senior researcher at ICEPRONAV in Romania, which was one of the centres of design excellence. And in that institute, he worked in the ship hydrodynamics department, which is basically the hydrodynamic of design ships, propellers, testing models, etc. Since Dr. Ganea has joined us, he's continued to provide consultancy services in ship performance and propulsion, as well as being lead researcher in the development of our ship handling and manoeuvring software. I'll pass you to Bogdan very shortly. This is the content of our presentation, so I'll just make a short introduction on the topic before handing to Bogdan, who will take you through the science of engine selection, engine layout curves, engine layout diagrams, and then I'm going to come and talk to you about model testing and the ship power sea trials, and then we'll then have a Q&A session. So before handing to Bogdan, I just wanted to emphasize the main theme of our presentation, which is how hydrodynamic performance clauses of a shipbuilding contract and specification relate to the science of ship propulsion. So I put up here on the screen a typical clause from a shipbuilding contract, which defines the guaranteed speed. In this example, 14.1 knots. But of course, that has to be in a certain condition. So the contract specifies that it should be at 12 meters, which is normally the design condition, and at a normal continuous rating of 7,200 kilowatts, with the propeller turning at 82.3 RPM and C margin of 15%. So basically, don't panic. This is the topic of the presentation. We want to take you through what all these various terms mean. So of all the various aspects of ship performance, speed is one of the most important. It's normally defined within the contract itself rather than the specification, with penalty clauses and how the contract is affected if the guaranteed speed is not met. So it's the reason it's so important is because the economic success of the vessel very much depends on its speed. If a vessel is not meeting its guaranteed speed, either it's going to have to consume more power to go at its design speed, or and of course more power means more fuel consumption, or it can operate at its intended power but go slower, which obviously means that it limits its revenue making capability. So obviously speed is extremely important, but also it's a very sort of difficult science. So that's what we're going to try and unravel for you now. So I'll hand you over to Bogdan, who will explain what these various terms mean.
All right, Kieran, I'm taking the wheel now. First of all, I introduce the concept of the engine layout diagram. The main propulsion engine is actually the power station of the ship, providing mainly the ship propulsion and also some other energy necessary aboard. The main parameters defining the engine operation are the power, which is in this diagram is plotted on the vertical axis, and the shaft revolution speed, or simply RPM, which stands for revolution per minute, which is plotted on the horizontal axis. The engine layout diagram describes the possible combination of power and RPM an engine is able to produce by its physical construction. The pressure created inside the engine cylinders by fuel burning process is quantified by the mean effective pressure parameter. The same mean effective pressure can be realized at various RPMs. The variation of the mean effective pressure and the RPM between certain limits define the engine layout diagram, which is this blue parallelogram. These limits are represented by this 4 points identified by L1, L2, L3, and L4. I'm going to describe these points, the signification of these points. The most important one is L1 on the upper right corner of the parallelogram, which is the maximum power an engine is able to deliver by its construction. This power is named the nominal maximum continuous rating, or abbreviated NMCR. It corresponds to the maximum effective pressure and maximum RPM the engine can produce. The engine can run at its maximum RPM, but at a reduced mean effective pressure, which define the vertical line on the right side of the parallelogram, L1 and L2. Point L2 corresponds to, in this example, to 80% of the maximum effective pressure. Point L2 is on the lower right corner of the parallelogram. Equally, the engine can run at its maximum mean effective power, but at a reduced RPM. And this operation is described by the upper diagonal line L1 to L3. Point L4 is diagonally opposite to point L1. And this means the engine runs at its minimum mean effective pressure and minimum RPM. The engine power, as it is naturally, varies with both mean effective pressure and RPM. An engine with its nominal maximum continuous rating, meaning point L1, is selected according to the requirements of the design. This consists in power requirements, space limitation, cost, owner's preference for operation, for the kind of operation the ship is intended. It is not necessary, the engine to operate exactly on point L1. Any selection of the maximum power engine is going to produce Any such selection below L1 is called a derated engine. Any derated engine, which is a common practice, has a lower specific fuel oil consumption, or abbreviated as FOC, and consequently lower greenhouse gas emission. Engine derating is accomplished by modifying the engine ancillary equipment like turbocharger and fuel oil delivery system. The selected power, as described above, is called specific maximum continuous rating, or SMCR. Sometimes it's called simple MCR because from now on it becomes the maximum power an engine is able to deliver. Now I'll pass to describe in more detail SMCR and how to in the position inside the engine layout diagram. This is on the next slide. For the same, or in other words, for this given SMCR or selected SMCR, various engines can be selected. You may see here 3 selections for the same SMCR, which is point MP. The power varies approximately with the cube of RPM, which means RPM rises to power 3. This correspondence or correlation is called sometimes engine power law. Once SMCR is established, the power versus RPM curve passing through SMCR or point MP is called the engine layout curve. It is the engine operation curve, assuming some additional power due to a real-life condition, which is known as heavy condition. I mean, in this so-called heavy condition, the engine should operate on this engine layout curve. A propeller operating on the right side of the engine layout curve, it is in a light operation condition. And on its left side means overloaded operation condition. It's exactly what I said before. I mean, it is desirable the operation point, meaning the combination between shaft speed, RPM, and the power, to not be on the left side of the engine layout curve. Maximum desirable is to be on the engine layout curve. The power versus RPM curve for a brand new ship sailing in ideal condition is called the light propeller curve. This is this curve on the right side of the engine layout curve. It is ideal condition means no wind, no wave, no current, deep water, brand new ship hull, and propeller, also the equipment inside the ship. It is also called trial condition. It is merely a theoretical notion because it is true only after the actual sea trials condition has been corrected for any wind, waves, water depth, and other influences, which is almost impossible to not exist in the real life of the ship in a real condition. The heavy and light propeller curves run almost parallel, and at the same power, the RPM is higher on the light propeller curve. This is due to the light condition under which the propeller is running, meaning less torque is required. For example, at point LP on the light propeller curve, the engine produces the same amount of power as in MP, but at a higher RPM. Points PD and PD' on the light propeller curve are propeller design points, which are to be, I'm going to explain further in the next slides. Now I introduce another notion, engine margin. Here in this slide, I provide an example of a contract clause defining the engine margin on the top right-hand side of this slide. Notice a stipulation of a guaranteed speed at only 90% MCR, which is actually 90% SMCR according to the notion or definition of terms introduced before, meaning that a 10% engine margin was applied. Engine operation margin, or simply engine margin, is a power reserve assumed for economic engine exploiting, meaning low fuel consumption, low greenhouse gas emission, and low engine maintenance cost. It's actually a reserve assumed to protect the engine. This reserve can be used, however, in an emergency situation. The idea is that in normal condition, to not operate the engine at its maximum power, SMCR, I mean on the point MP on the engine layout curve or point LP on the light propeller curve, but at somewhat reduced power, usually by 10 or 30%, something between 10 to 30% of SMCR. 15% being used. Here it's a debate. In the past, 15% was most frequently used. Today, a figure as 10 could be found as well. This reduced power defines the normal continuous rating, or NCR. Sometimes call it continuous service rating, or CSR, which is the power on point SP and PD prime on the engine layout curve and light propeller curve respectively. Another notion in ship propulsion or ship design propulsion is a light running margin, or LRM. On this slide, you can see an example of LRM clause from a shipbuilding specification, which reads as follows. The propeller pitch shall be designed to absorb NCR power at NCR RPM with about 5% margin in RPM at the design draft in calm sea and with clean hull conditions. This defines, as I said before, the ideal condition. Propeller light running margin, or LRM, is a propeller additional RPM assumed in ideal condition on top of that in heavy condition, expressed on the propeller design point on the light propeller curve, PD or PD prime. It is an RPM reserve assumed in ideal condition to ensure that in heavy conditions the engine will operate on the engine layout curve. If this does not happen, and the engine were to operate on the left side of the engine layout curve, once the C margin is applied, the engine will be overloaded. In this case, the propeller is called heavy in the hydrodynamic sense. This means that the assumed LRM by design was not appropriate, was insufficient actually. If this happens, the propeller still can be slightly corrected by adjusting the blade trailing edge or clipping its tip to reduce its diameter, or both, combination of both. Even so, it is highly undesirable due to additional cost and because it is not always really successful. LRM is expressed as a percentage of the engine RPM on the engine layout curve. Engine RPM on light propeller curve is calculated by this relationship, where LRM is expressed in percentage. The values recommended today are 4 to 10%, which are greater than the former recommendation 3 to 7%. These recommendations are both from MIN Energy Solution, which is the largest energy manufacturer. I can describe this relationship. So it is N light should be N heavy times 1 plus LRM. The relationship is visible on the right side of the diagram in this slide. Finally, I will introduce the C margin. Here in this slide, there is an example of a contract text which was quoted earlier in the part presented by Kieran, stipulating the guaranteed speed at NCR with 15 C margin. The C margin is an additional power assumed on top of an ideal condition. Therefore, on top of the power in ideal condition. Therefore, on the light propeller curve, in order to ensure the ship speed performance in a real condition, since the propulsion was designed from the data of an ideal condition. The ship speed in ideal condition is called trial speed, and that with C margin assumed is called service speed. Both are contractual items mentioned in the building contract and technical specification document. Here I must say that the most frequently used is the service speed, because this is the most relevant than the trial speed, which is only achievable in ideal condition. The C margin is expressed as a percentage of power in ideal condition. The recommended values are between 10 to 30%, 15 being frequently adopted. On the diagram, the point PD on the light propeller curve is the power in ideal condition during the design process. I mean, use it during the design process. By adding the C margin on top of it, the power on PD prim is obtained. The calculation relationship with C margin in percentage is visible on the right side of the diagram. It's pretty similar to that of the LRM. This power should equate the engine normal continuous rating, which is the point LP on the light propeller curve, or point NP on the layout curve. I'm afraid here it's a slight error, because the NCR corresponds, as I said before, to SP point on the engine layout curve, and PD prim on the light propeller curve. By doing so, the power required in service condition, which means real C, therefore heavy condition as introduced before, will not exceed that provided by the engine operating normally. The remaining power reserve, assumed by adopting the engine margin, which I was explained before, may be used in exceptionally heavy condition, for example, in a very rough sea. Now I'll hand the microphone to Kieran to continue to explain the importance of the model tests and sea trials, which are part of propulsion design process. Kieran, please.
Okay, thanks for that, Bogdan. I'm now going to talk to you first about model testing, which is an important part of the design process. It's when hull form is finalized and the propeller is designed, and this is to ensure that they operate efficiently and also meet the design requirements in terms of installed power. So although it's a design topic, it's important to understand model testing if you're going to understand the process of sea trials and verifying the as-built design, which is an important part of the ship delivery process. Model test comprises of a scale model. I've shown a couple of examples here. Accurately built of the vessel, and it's typically as much as 10 meters in size. Scale factors for larger model basins can be 1 in 20 or 1 in 25. So basically, the larger the model, the more accurate the results, and tends to be the more modern basins are the largest ones to get the highest accuracy. The model basin itself is essentially a long trough of water indoors. Larger basins are anywhere upwards of 200 to 300 meters long, and they can be very narrow if they're specializing in propulsion testing. Propulsion basin can be as narrow as 10 to 12 meters. And this is fine because essentially we're just testing the vessel going forward. We're not doing maneuvers, etc. The equipment in the model basin, the main part is the carriage, which is electrically driven carriage, which goes down the model basin on rails. You can just see this man here kneeling on the carriage in this case. In some tests, the carriage tows the model along, and in the self-propelled test, it also provides the power for electrically driven propellers and a platform for measurements to be taken. Model testing in a ship propulsion requires a number of tests. It requires a self-propelled test, where a scale replica of the propellers are put on board the vessel, and the vessel is moving down the tank, and the torque required to turn the propellers is measured by dynamometers. I've included a couple of model test dynamometers here on the right. And the propeller revolution speed is also measured, and multiplying torque by the revolution speed gets you to the delivered power. Another test required is the resistance test, where the hull alone is pulled down the tank by the carriage, and no propellers are fitted to the model. And also there's another test called propeller open water test, where the propeller alone is towed along the tank without the presence of the hull. And that's basically to calculate the performance of the propellers in conditions when the hull is not there. I show an example of the equipment for an open water test here. So those are the tests that are required to calculate the full-scale performance of the vessel. The reason why there's 3 sets of tests, when one might think that all you had to do was a self-propelled test and then multiply the measured power by a factor, is because obviously we're measuring at model scale, but we want to make a full-scale prediction. So the power at the model scale is not interesting to us. We want to know what the power is for the actual ship. But the problem is that the various components of the total power don't scale according to the same laws. So unfortunately, you can't do a simple multiplication. You need to scale each of the components of ship resistance and ship propulsion separately, and then recombine them one scale to full scale to make a full scale prediction. But that tends to be taken care of by the model base, and that they'll have software for doing that. Another type of test which is often done is wake measurement, and this is a measurement of the water velocity past the propeller disc, and it's used for propeller design. It's not actually part of the calculation of full-scale power requirements. An example of model basin setup is shown here on the left-hand side corner, where there's a velocity probe positioned in way of the propeller disc, ready to go into the water. So I'd like to show you now what the end result of a model test program, once the various tests have been performed. So that gets performed at a number of different speeds, and the model basin produces a speed power RPM diagram or graph, an example of which I'm showing on the left-hand side of this slide. So this left-hand vertical axis is the power from which, and this is the power curve, the lower one. So you can read the variation of power versus speed off of this curve here. And on this axis here is the propeller RPM, and this is the propeller RPM curve. So again, you can see what the variation of propeller RPM is with surface speed. So how do we interpret this particular diagram? As previously described by Bogdan, the NCR, the normal continuous rating, is the engine power calculated from the SMCR value with the engine margin included. In this particular example, it's 7,448 kilowatts. So that's once it's had the 10% engine margin taken off of it. There's a further reduction of 1%, so that's why that's multiplied by 0.99, and that's for transmission losses. So between the engine and the propeller is a shaft with various bearings, and some of the power is lost due to friction in the bearings, 1 or 2%. It's normally a small factor. So the NCR power delivered to the propeller in ideal conditions, which is basically the conditions of a model basin, then we can read off what the speed is predicted in ideal conditions. So following this line here, for the NCR, where it meets the power curve, we can see that happens at 14.83 knots. As described by Bogdan, there's the idea of a C margin, typically 15%, as it is in this example, to allow for the effects of environment and hull fouling, etc. So the power that the NCR power is reduced by a factor of 1.15, and also there's still that transmission loss to arrive at a power in this case of 6,412 kilowatts. So drawing that line at that power level and dropping down, we can see that the service speed, including the C margin, is 14.35 knots. And this is the speed which typically the contract is based on. The other feature of this graph that I'd like to show you is how you can use it to calculate the light running margin, as described by Bogdan. The light running margin is the difference between the propeller revolution speed on the light propeller curve in ideal conditions and that on the engine layout curve. So determine that. All we have to do is define the propeller speed at NCR power on the light propeller curve. So previously I showed you how the trial speed of 14.83 knots can be determined from this diagram. And following this vertical line at 14.83 knots upwards till it meets the RPM curve, and then reading across, you can see that the propeller will be turning at 87.82 RPM. And in this particular engine, it's not shown on this graph, but the NCR revolution speed is 82.4 RPM, which means that there's a 5.42 RPM margin or difference between those two values. And expressing that as a percentage of the NCR propeller speed gives you a light running margin of 6.6%. Okay, just to make some final closing comments on the speed power diagram, speed, of course, is one of the most important parameters of the ship. Normally defined in the contract, but LRM is always specified in the specification or any of the contracts I've seen. The implications of a ship which is too slow or demanding too much power are obvious, but the LRM effect is a little bit more subtle. With a ship with a low LRM can have difficulty punching through adverse weather, and it can accelerate sometimes very slowly, which causes trouble with maneuverability, and sometimes means that the engine shaft is spending too long inside the barred speed range when it's going from maneuvering or from slow to full speed ahead. So there's an analogy often made between the gearing of a car and a ship's LRM. Essentially, a vessel with a low LRM is similar to a car which stuck in high gear. Essentially, it can travel at high speeds, but it lacks acceleration or it lacks ability to go uphill. And in a similar way, an LRM has difficulty punching through difficult weather or getting up to speed. However, although in ideal conditions, it can actually achieve the speed once it's there. But anyway, as mentioned by Bogdan, it can actually be corrected if it's found to be deficient in a sea trial. Okay, so we now come to the sea trials. So the sea trials are an important part of the verification process of a new design, and it's here basically where the designers finally test it against those important aspects of the contract and specification. The part of the sea trial I'm talking about here is the speed power sea trial, also known as the progressive speed sea trials. There are, of course, a large number of tests that are done at sea trials, such as endurance trials, testing of machinery for the ship. But the speed power sea trial is when the hydrodynamic performance of the ship is actually tested. The conduct and analysis of the sea trial is typically done to a standard. The most commonly applied is the ISO International Standards Organization 15016. The 2002 version of that was used for many years and was recently updated in 2015. The recent update was at the request of the IMO's Environmental Protection Committee, which was implementing at the time the EEDI legislation. Because the EEDI takes the input power requirements of the vessel, then it was a requirement to make a robust standard that can be consistently applied. Some of the difficulties in the past with correction of sea trials is that procedures were often open to interpretation, and where there were marginal performance issues, then potentially there would be a difference in interpretation between ship owner and shipyard. So recognizing the difficulties of that, and especially when it comes to statutory regulations like the EEDI, then the MEPC asked the International Towing Tank Convention, ITTC, to propose a new set of rules. The ITTC produced this document here, which is the basis of the ISO standard 2015. So the ISO 15016 defines how the speed trial should be conducted, what the maximum weather conditions are, what the water depths, duration of runs, etc. It requires that reciprocal runs be performed. So that's basically one run with the wind and one against the wind. And it specifies various measurements which are required. That's the RPM of the propeller, and also the torque applied to the propeller. Torque is normally measured by putting strain gauges on the propeller shaft and measuring the material stress. So once all those measurements are performed, the ISO standard defines how they're to be corrected. Essentially, as Bogdan mentioned, rarely can a sea trial be performed in ideal conditions, meaning absolutely no wind and absolutely no wave. So they have to be removed by calculation, and that's defined in the ISO standard. In the past, the methods of correction used were fairly widespread. Shipyards and testing companies would have their own software or their own spreadsheets for performing these calculations, and it led to various differences between the various institutes that were performing these tests. So as part of the standardization of sea trials, the developers of the newest standard, which was the STA group, which was a subgroup of the ITTC, developed software which they called STAIMO. The leaders of the STA group were Marin in the Netherlands, and essentially STAIMO is their software, although it's freely distributed. The software is able to take the results of the speed power sea trial, they're entered into the piece of software into STAIMO, and what comes out are the corrected sea trial results. So although it's been a very good step forward and widely adopted in the marine industry, yeah, so I mentioned one or two issues that are arising later in this presentation, but STAIMO is a very good step forward with standardizing sea trial performance. A particular wrinkle of the sea trial process is that for many ship types, most notably bulk carriers, it's not possible to perform sea trials in the fully laden condition. Obviously, when the ship's produced by the shipyard, it's in an unladen condition. It hasn't had its first load of cargo. And so the sea trials are performed, the ship owner takes delivery. And that means that they're conducted in the ballast condition. However, normally the contract requires the guaranteed speed at the design draft, basically fully laden. So the approach taken by the ISO standard and most of the standards is to essentially use the sea trial in the ballast condition to check and calibrate the model test results. So if there's a correction to the power predicted for the model basin in the ballast condition, then the results are corrected by a calibration factor for the fully laden condition. It's not ideal, but it's basically how bulk carriers and other vessels are tested. It's sort of the model basin result calibrated to the sea trial rather than a pure prediction at sea trial. And just to show you briefly what the end result is, I show example outputs from the results from STAIMO. And this is essentially the same curves we saw earlier for the model basin, except these are for sea trial, corrected for the effects of wind and waves, etc. STAIMO produces these plots, these 3 plots rather than a combined plot, but the same information could be taken from these plots. So STAIMO also provides the various parameters required in the contract, such as LRM and service speed, as output, so you don't have to read them from these diagrams. So to make some concluding comments on what the state of the art in the industry is in terms of the conduct and analysis of sea trials, as mentioned previously, the adoption of ISO 15016 2015 and STAIMO have been very positive in standardizing the approaches. However, we're still seeing shipbuilding contracts which specify other correction methods. Even the BSRA 1978 method is sometimes applied. This is despite it being a requirement of the MEPC resolution 261/68 for the EEDI calculation, which requires the latest ISO standard to be used. There are other aspects which are not quite following the ideals of the 2015 version, and that's the process of model trials. The standard requires that model tests be done by the propeller load variation method, sometimes called the British method, and that basically requires that for every single ship speed, there are a number of runs done at different propeller revolutions. And that extra data is required to be used in the newest version of the standard. We're still seeing that most model tests are using single runs at 1 propeller RPM, sometimes called continental method. As a result, there's important data lacking from the analysis of the sea trials. So STAIMO has a workaround for this problem, as it provides default data within STAIMO that you can use, and generally that's accepted by owners and shipyards. However, they don't take into account the specific ship type and the design of the particular vessel that's being tested. And in our experience, the appropriate values are somewhat different depending on those effects. So although in principle the 2015 version of the ISO standard should have been a technological step forward, in some ways it's a step back from the previous version of the ISO standard, not because of the standard itself, but rather how it is implemented in the conduct of model tests, which was recommended by the ITTC. So that's the end of our presentation. Can hand you back to Adam to see if there's any questions that have been asked.
Thanks, Kieran. Just before we start the Q&A session, I must apologise to those who haven't been able to send them in. We are experiencing some technical difficulties with the Q&A session. I think there's a gremlin somewhere. But if you do have a question to ask and you haven't been able to send it through, if you send it to the email that you registered to attend the webinar, so if you email it to marketing@brookesbell.com, I'll make sure that it's forwarded to Kieran and Bogdan and they will reply to you with an answer. However, some have managed to get through. Regarding the sea trials, if trial runs are performed on reciprocal headings, why must any corrections be applied?
Okay, yeah, that the idea of reciprocal runs is not to eliminate the error entirely. So you might think simplistically that if you do one run with 15 knots and one 50 knots wind speed and with one run against, that the effect on power would cancel each other out entirely. In fact, it doesn't work exactly like that mathematically. And of course, there's no guarantee that you might have had a 20 knot following wind, and then you had a 10 knot adverse wind during the runs. So although the reciprocal runs reduce the size of the corrections, it does not eliminate them entirely. So you always have some correction that still needs to be deducted by the calculation afterwards. I hope that was understandable.
Okay. Is the wake measured with the propeller in action? And if not, why? And what are the consequences?
Actually, I think that's a good one for Bogdan, as a former model basin expert.
No, actually, what is called by wake measurement is carried out without propeller. Here it's a lot to discuss. We have to make distinction between the wake of the model scale and that of the ship scale. So first of all, the wake from model scale is transposed by some procedure to the ship scale. This is because the flow in the aft part of the ship is not exactly the same as the model. This is what is called scale effect. Further, it is to calculate this is nominal wake, what is called nominal wake. For propeller design, it is called it is used effective wake. Effective wake is obtained by subtracting from this nominal wake the velocities induced by the propeller itself. So it's somewhat more complex.
So I think, Bogdan, there's essentially two wake values.
Yeah.
There's the nominal wake, which is without the propeller, used in ship design, and effective wake, which is the wake with the propeller, which is used in the propulsion.
Effective wake is not the velocity's existence behind the ship when the propeller operates. It's merely a theoretical notion. I mean, from the velocities with the propeller in operation, you subtract what the velocities induced by the propeller itself. While the nominal wake is what's happened without propeller action.
Yeah. Okay, I think.
I hope I was enough correct because.
Yeah, it is that's a very challenging question, I have to say.
Yeah, it is. If the notion of effective wake comes from the self-propulsion test.
Yeah.
And what's happened when a propeller open water diagram is introduced. It's effective wake is what the velocity seen by the propeller. Yeah. You see in more plastic, it's the input velocities to create the propeller thrust effect.
Yeah. I think
in front of a whiteboard or blackboard, we could discuss better than this our webinar.
I think that's as simple as we could have made that answer, Adam. I'm scared that we're going to go. It's going to get more complicated if we go further.
Okay. So just conscious of time as well, we'll just take one more. Why does ISO standard 15016 version 2015 require the British method?
Yes, this new standard aimed to improve the method used by the previous standard in 2002, which is based on the method developed in the 60s. That method developed in the 60s is called the Taniguchi-Tamura method. That method is not bad by itself, but unfortunately is a standard in 2002. Followed what exactly, the procedure of Taniguchi-Tamura developed on the time of slide rule and graphs designed by hand. All right, so besides this, to introduce this new tool, the computer, on particularly the PC computer available for everybody, this new standard aimed to take into account the variation of the propulsive coefficients determined by the self-propulsion test due to the loading or overloading propeller of the propeller. The previous method, the previous Taniguchi-Tamura or ISO 2002, is based on the results in calm water. The continental method, so-called continental method, determines how the propeller operates in ideal condition. The British method, by its process, tries to determine what's happened when the propeller is overloaded. Close to the real environment operation. So beside those propulsive coefficients, the British method is able to determine how they vary once the propeller is overloaded. And this was implemented in the new standard.
So essentially, the British method will be testing at a range of conditions at different RPM, one of which will match the conditions of the model test with the propeller. It's
expected to match better the real condition.
Yeah.
By providing the variation of these propulsive coefficients, which the continental method is able to determine or to determine only in ideal condition.
Yeah. So I know we're running out of time, but Bogdan and I actually authored an article on this subject in the Royal Institute of Naval Architects, which it's not meant for this audience, but it explains a bit more about what the difference is between the two ISO standards, and make some suggestions about how you can still use the modern version of the standard if your model tests haven't been conducted using British method. So I can, if any of the audience would like to have that, we can send a copy of that to somebody. But the short answer is that the British method means that the condition that the model tests were that the sea trials were conducted in would be covered by the British method, but not by the continental method.
On the expense of time of carrying out the test.
Yeah, it takes longer.
We produced two papers. The last one in 2018 proposed, because unfortunately, as Kieran pointed out in our presentation, this new standard has its own drawbacks, and in my personal opinion, it is merely suitable for heavy loaded propellers. But on the other side, the heavy loaded propellers are encountered in particular applications like tugboats, trawlers, not in bulk carriers, which are medium loaded, moderate loaded propellers.
Yeah.
In other words, for moderate loaded propellers, the variation of the propulsive coefficients is not so impressive. And what's happened when the propeller is overloaded is okay, sorry. Okay, I have to leave the presentation. We have some domestic problems. Sorry, I could maybe be back in 5 minutes or so.
I think yeah, I think again we've reached the bottom of that answer anyway. Yeah. Adam,
we're saved by the bell.
Yeah. Yeah.
Right. Okay. We'll just wrap it up then, I think, and thank Kieran and Bogdan for presenting to you today. But more importantly, thank you for attending, so they had somebody to present to. As I have said, apologies for the technical difficulties with the Q&A, but if you do have a question that you would like answering, do email it to marketing@brookesbell.com, and I will make sure that it's passed on to Kieran and Bogdan. But all that remains for me to say is thank you, and enjoy the rest of your day.
Thank you.